Everyone loves the challenge of trying to solve puzzles and enjoys the satisfaction of accomplishment when they do solve them. I have seen first and fifth graders solve 3x3 magic squares in doodling while waiting for the commencement of the exam. I have seen struggling students solve complicated magic square puzzles as they persistently try and try again. I've watched first and second grade students solve magic squares while their teachers look on in amazement. Using the magic square as a paradigm, I shall illustrate what students need to do to enjoy and understand math. Ask questions. We begin with the 3x3 magic square. Given a set of 9 numbers, arrange them on a tic-tac-toe board such that they add up to the same number in all directions. It could take an adult a long time before they could solve this problem. But you could take a pre-K student and they could solve it in a few minutes if you give them a little instruction. You'll note in the yellow squares that even numbers are in the corners and the odd numbers are not in the corners. And we can look 2, 4, 6, 8, 1, 3, 5, 7, 9, a relatively easy pattern to recognize. I've shown this to many, many kids, but none of them, or few of them, ever ask the question, why do they add up to 15? And you can lead them in a very easy direction. If you sum up all the numbers from 1 to 9, they add up to 45. And if you take 3 columns, and each column has to be the same number, then 45 broken into 3 parts gives you 15 per column. It's that simple. But that question gives us insight and leads us on to more things. Another question that they don't ask, is that the only answer? Well, no, it turns out there are 8 answers. If you look at the first one, it's the pattern that we showed in the previous slide, and the next one is the pattern flipped in the other direction. And then we merely go through several rotations to get the other solutions. So we're making use of a concept called symmetry. But none of them ever ask, are there more than one solution? So these are questions in terms of the curiosity that lead us on to discover other things. Okay, so there are 8 solutions. Okay, and here's a process that even a kindergarten student could go through to show that there are 8 solutions. You write a column of numbers. The first column starting with 1, then 2, and all the way up to 9. And the second column have the numbers run from 1 to 9. And then we have no choice in the third column. It has to be a number such that when added to the first 2 numbers, we get 15. And if we go through that, we can begin to cross off solutions that are not possible. For example, we don't have numbers bigger than 10, and we don't have a number more than once. So as a result, when we finish going through this process, we find that there are 8 chains. And if we then put a box and count how many are in for each number, there are 3 for the even numbers and 2 for the odd numbers, except 5, which has 4 numbers and is in 4 chains. And if we look at the geometric solution on the right, we see a number in the corner has 3 chains going to it. A number in the middle of the edges has 2, and the one in the middle has 5. And there we are. Now we know why even numbers are in the corner. There are many more questions to ask. I'm leaving you to figure out what those questions are. However, the next thing is, how would we do a 4x4 magic square? Well, in this case, we create another pattern. We put dots in the corners. Corners seem to be our favorite thing. And in the middle, we put 2 dots. And so then we count along. 1, we see a dot or a yellow square, we put a 1, 2, 3, 4, we see a yellow square, we put a 4 in it. 5, 6, we see a yellow square, we put a number. We continue all the way down to the last square. Then we count backwards. If there's a number in there, we don't put another number in there. So 1 at the 16th place, no. 2, 3, no. 4 at the 13th, 5, 6, 7, 8. We finish, we now have all 16 numbers. And again, nobody asked the question, what do they add up to? Turns out if we use our formula, we will find that they add up to 34, using the same logic of what do the 16 numbers add up to, and that we have 4 columns. However, this one is a little bit more interesting in that there are over 7,000 solutions, 7,040 to be more exact. However, I found I could find 1,152 solutions making use of symmetry and something called group theory. And what you see on the left is a series of 4 objects. put it in the top box, and the same on the right. And then what I have the puzzle do is to be able to figure out what goes in the rest of the rows such that there is not two letters of the same in a row, column, or on the diagonal. And now if I set these to a permuted set of numbers, I can now get my left and right square, combine them together, as you see at the bottom, and then add those numbers together, and they will add up to 30, but if I add 1 to each column so that the 0 disappears, they will add up to 34. So here is a way of finding solutions, and I haven't found them all. So this is something that you can do beyond what I've done. Okay, then we move up to the 5 by 5 magic square. The trick is we start in the middle. We always move on a right diagonal. We come down when we're off. We continue on a right diagonal. We're off the board. We move to the other side, and we continue until we see a number there. In this case, we just drop down below the number that we were at and continue the process until we get to this square in the corner. And in this square in the corner, we consider that a block, because if we went off, we would discover that there is no place to receive us coming down. So as a result of that, we now can find the solution to this. Now, this one is also interesting in the sense that I found in playing some games that I did with a 4 by 4 magic square, I could find 86,000 solutions. But in this case, I made use of the numbers in the square to help me come up with these templates. This one was particularly interesting because I thought I had a universal solution, worked for 3, 5, 7, 11, 13, but it didn't work for 9 and 15, which are not prime numbers. So one has to be very careful when they come up with solutions and figure out the way to check them. In fact, this is the other part of learning and creativity. You have to make mistakes, and you have to be willing to look for those mistakes. This is something which I found a lot of students don't seem to really appreciate. Okay, then we go to the 6 by 6 magic square. Well, at this particular point in time, we have to come up with another rule, but not quite as difficult as you might think it would be. We now group these in groups of 4. So now we're reduced down to a 3 by 3 magic square, and we use the same rule for moving these. But when we put these 4 in, they can be put in either an X pattern, 1, 2, 3, 4, or they can be put in what I call a backwards U pattern, 5, 6, 7, 8. And you see where I have the backward U pattern. But the question is, how did I discover those patterns? Again, a question that's not asked. And I've got many, many students who have never asked that question. By now, they know where these numbers at the bottom have come from. Okay, and it turns out that what I did was, as I noticed when I put these numbers in just using an X pattern, I found that on the horizontal direction, they both add up to 5, but they add up to different numbers on the vertical direction. And so when I started putting these in, I was getting an excess over 111 or an undercount from 111 in this direction, but doing fine along this way. So I then created another set of patterns, the forward U and the backward U. And now when I looked at what they add, I looked up in the excess of 5. For the X pattern, I had 1 less than 5, but for the Y pattern in that direction, I had an excess of 2. So that led me to believe that in the vertical direction, I have to have 2 X patterns for each Y pattern. And that logic then went on to find out that I also needed 2 Ys in the diagonal direction for each X. Okay, so now we have enough information that we can now do any magic square. Okay, the 8 by 8 magic square, we basically put 2 4 by 4 magic squares together, and we basically, after we put the dots in the appropriate places, we count right across like we did before. And now you also know why these add up to 260. Okay, and then 12 by 12, 16 by 16. We're doing great guns. But now we get to a 10 by 10 magic square. But it turns out there's an interesting solution built upon all of what we have done. The squares that are in light yellow and the white squares are all what I call X patterns. The squares in orange or a dark yellow are what I call the backward U's or the Y pattern. And the blues are the Z patterns. And what happens, we found that the Z's and the Y's match each other. So I could put these in any order, just as long as I have the same number of Z's as Y's. Over here, you can see the 6x6 magic square, and you see it again, except we have an overlap. And now again, using the rule, we have to have 2 x's for y in this direction, 1 x for y in this direction. And now we've solved the 10 by 10 magic square. And just to test this out once more, we go to the 15 by 15, again using the same color scheme. But we see that in this particular case here, that we no longer have the overlap, and we have this region in here in which we have 2 x's for a y. And as we get to bigger and bigger multiples of 4, that we find that we have this separation region getting bigger and bigger. And as you might guess, we can put this I-bar in any one of these positions to satisfy, the rules for the x, y's, and z's. So this is basically taking a little bit of information, asking a few questions, and now we can solve any magic square problem without having to memorize huge amounts of rules or taking notes. Initially, when I started this project, it took me hours in order to get these other squares because I didn't have the rules well organized. So here you are, the road to creativity. Just ask questions.